Okay. This is a review of most all of the probability sections of AP Stat. Some of the more introduction to probability type stuff and or probability equations, and diving deeper into some expected value stuff, combining standard deviations, binomial geometric distributions, normal distribution as a probability function, things of that nature. In the description to this video, you will find a link to a PDF file that contains the problems that I will be going through today. So with that, let me get the first problem set up here. There we go. I am going to be writing on this worksheet to put some of those answers in. Hopefully I'll be able to fit some stuff into the side and whatnot, but we'll see what happens from here. Number one, what is the probability that a student from this class eats breakfast but does not floss their teeth? Now, they give you a whole description in the beginning, which I'm going to get to in a moment. But a problem like this, what is the probability that a student from the class eats breakfast but does not floss their teeth? This is not a straightforward and or problem. This is not a straightforward and or problem. What was incredibly helpful with a problem like this, if you are able to create one, is to create a Venn diagram. Now I'm going to try to create a little bit of a Venn diagram to the side right here, in which one of those circles would represent breakfast and one of those circles would represent flossing. There we go. Move that over just a tiny bit. There we go. It says 57% of students eat breakfast in the morning, but that is a combination of everything in this section of the circle and what is in the overlap. In 80%, same deal. 80% is this entire circle, which contains the larger portion of it and the overlap. 46% of students eat breakfast and floss their own teeth. That's where I'm going to start with this. 46%, right in the middle, barely legible. That's okay. Which means that in this portion right here, this has to be 11%. As you can see right there. 11% and 46% added together make 57%. 57% of students eat breakfast. And it says that 80% floss their teeth. So this should be 0.34 because that is going to add up to that 80%. Now we can go about, if you have a structure like that, you can go about answering the next number one. Just as a side note, those three probabilities, they add up to 91%. Altogether, there's 100%. We're missing 9%. This 9% is the percent of people that do neither, that do not eat breakfast and do not floss their teeth. Venn diagrams are very helpful in this regard. So, back to number one. What is the probability that a student from this class eats breakfast but does not floss their teeth? That would have to be 11%. Number two, what is the probability that a student from this class eats breakfast or flosses their teeth? Now, there's two ways to go about this now. Two ways. Number one, because of that word or, you can go about using the following formula. The probability of A plus the probability of B minus the probability of A and B, in which the numbers given to you in the instructions would be sufficient to answer that question. You could go 57% plus 80% minus 46%. And just for the sake of argument, 57 plus 80 minus 46 gives you 91%, as you can clearly see. Another way of thinking about it, what is the probability that a student from this class eats breakfast or flosses their teeth? that would be everybody within the Venn diagram. These people only eat breakfast. These people only floss their teeth. And these people do both, all three of them combined, 91% answer that question. Number 3, 5 juniors and 4 seniors have applied for 2 open student council positions. School administrators have decided to pick the 2 new members randomly. What is the probability that they are both juniors or both seniors? Being that this is an or probability, we are going to have to add something together. As a reminder, and I should have said this with the previous one, when you're dealing with or, it is in reference to addition. And if you're dealing with and, it is in reference to multiplication. Now, it may not be necessarily that straightforward of, oh, yes, I have to do exactly that. There may be some quirks in between with the problems, which we'll deal with when we get to them. But for the most part, this is the mindset that you need to have. You have to find the probability of getting both juniors and then add, is that word or, you add the probability of getting both seniors. Well, 5 juniors, 4 seniors, altogether 9 students applying for 2 open council positions. If they're both juniors, that would be 5 out of 9 times 4 out of 8. And the reason why that fraction changes in the denominator, well, mostly numerator and denominator, is that a student was chosen, a junior assumed to be chosen. So this would be a junior being chosen and then a second junior being chosen to fit that both juniors. Now for seniors, same situation, except there's 4 seniors. 4 out of 9, 3 out of 8. If you do that calculation correctly, you should end up with 0.4 repeating, which the answer would put you at B. I can show you that calculation here. 0.4 repeating, which obviously they rounded, or a fraction if you wanted to, 4 over 9. Number 4. A fair coin has come up heads 10 times in a row. The probability that the coin will come up heads on the next flip is. Now, this has to do with the law of, well, I should say the fake law of averages. There's no such thing as the law of averages. There's no such thing as being due. If you flip the coin 10 times in a row heads, you might think, well, I'm due to get tails now. There should be a better shot of getting a tails now. Every single trial, every single flip is independent of the next, which means the coin, the probability of getting a heads or tails, the probability resets every time you're ready to start a new flip. The coin has no memory of what happened beforehand. In number 3, we had to change that probability after we got that first junior. There were a finite number of juniors, and each selection of a junior is actually dependent on the next. Be careful with that. In this fair coin, every flip is independent. The answer has to be B. No such thing as being due, no such thing as the law of averages. 50% chance each successive time. Now, if you wanted to answer the question, what are the chances of getting 10 heads in a row? We can have that conversation. If it was the probability of not getting a tails until the 11th flip, again, that's a different conversation. But the question specifically asked the probability that the coin will come up heads on the next flip. It's got to be 50%. Readjusting the paper, we're looking at number 5. According to the National Telecommunication and Information Administration, 56.5% of U.S. households owned a computer in 2001. What is the probability that of 3 randomly selected U.S. households, at least one owned a computer in 2001? Now, this question can be answered in 2 distinct ways, but they get the exact same answer, of course. With this problem, they're talking about at least one owning a computer, meaning they want the probability of getting 1 owning a computer, or 2 owning a computer, or 3 owning a computer. Now, it is entirely possible to do something like that, but you have to keep in mind a lot of the combinations that there could be with the 3 people. For example, if one owned a computer, is it the first one, the second one, or the third one that owned the computer? You have to take into account all those cases. Instead, the easiest way to think about this, if you want to find the probability of at least one owning a computer, you would prefer to do 1 minus the probability of none owning a computer. There are only, if you think about it in terms of the number of people owning a computer, there are only 4 possible outcomes. It's either none own a computer, 1 own a computer, 2 own a computer, or 3 own a computer. And they want this probability right here. They want 1 or 2 or 3. So instead of doing that, we find the probability of none and do 1 minus. Altogether, those 4 possibilities add up to 100%. They should. So if there's a 56.5% chance of that person owning a computer, that must mean that the probability of not owning a computer is approximately, what I write down, 0.435. So if you did 1 minus 0.435 times itself 3 times, which would be the first person not owning a computer, and multiply the second person not owning a computer, and third person not owning a computer. Oh, you can't see that calculation. I'm going to move that over. There we go. Much better. That would be 0.435 times 0.435 times 0.435, and then doing a 1 minus. We end up with approximately 91.8%. Answer Z. Another way of looking at the problem, considering the fact that this is a Bernoulli trial, and I'm going to talk a bit more about Bernoulli trials in a later problem, but Bernoulli trials either come down to one of 2 outcomes, a success or a failure. And in this case, the success is owning a computer, and the failure is not owning a computer. This is a Bernoulli trial. Each person owning a computer independent of the next person, et cetera, et cetera, et cetera. Being that it is a Bernoulli trial, we can consider this a binomial because of the finite number of trials. There are 3 trials, 3 randomly selected U.S. households. With the way that binomials work, you do binomial PDF, CDF, it doesn't really matter. 0.565. I'll write this out and then explain what's going on here. Here we go. This calculation, I don't put an equal sign there. Anyway, this calculation, the binomial is looking at 3 trials in which there's a 56.5% chance of success, and you're looking at none of them being successful. It will calculate the chance of none of them being successful, and then because we're doing a 1 minus in front, it will calculate the chance of getting 1 or more. What I'm basically saying is it will get you the exact same answer that we did before. There it is, 91.8%. Let's talk about number 6. Now, with number 6, similar situation. According to the National Telecommunication Information Administration, 50.5% of U.S. households had internet access in 2001. What is the probability that 4 randomly selected U.S. households all had internet access in 2001? So we're looking at a 0.505 chance, or a 50.5% chance. All 4 of them being successful, being raised to the 4th power, get you approximately 0.065, which is 6.5%. Another way of looking at that problem would be thinking of it again as a binomial. But we're looking at getting 4 successes, exactly 4 successes out of 4 trials. Because of that, we're going to be doing a binomial PDF, PDF being getting it exactly that number of successes. 4 trials, chance of success, 4 successes. If we did that, go down here, there we go, binomial PDF, 4, 0.505, 4, spits, again, the same answer. I'm just going to put a little arrow right there. Let's talk about number 7. Which of these has a binomial model? Now, keep in mind, binomial, the 4 choices are the same choices as number 8, which is geometric. I'm going to have to separate those. To talk very briefly about a binomial has a finite number of trials, a set number of trials. Whereas a geometric is technically open-ended. It's like waiting to get that first success. I mean, you might say like, oh, what are the chances that I get that first success like within the first 8 trials or something like that? Or I only have 8 trials. What are the chances that I get it on the 5th try? Geometric, you're waiting to get that first success. With a binomial, you're trying to get a certain number of successes within a set number of trials. If you read the choices for number 7, it comes down to 2 main things, 2 main choices that people may go for, and they might go for C or D. A, B, the number of people until we find, I'm going to stop right there, until we find is implying a geometric. E, the number of soda students drink per day, that is not a number of trials that we're looking at. C and D is a set number of trials, but there is one definitive answer here. C, the number of people in a class of 25 who have taken statistics. D, the number of aces in a 5-card poker hand. For C, there'd be a class of 25 trials with either a success or a failure. In the poker hand, it would be 5 trials, and then looking for a certain number of aces. The answer is C. The reason why D is eliminated is because if you have a 5-card poker hand and you're treating it like a binomial model, then every outcome from 0 to 5 should be possible. There should be a chance of getting 0 aces. There should be a chance of getting 1, 2, 3, 4, or 5 aces, and therein lies the issue. No such thing as 5 aces. Getting 5 successes in 5 trials should be possible in a binomial model. But for D, it's not. You can't do that. No such thing as 5 aces. Number 8. Now for number 8, I had already implied that it came down to A or B because we're waiting until we get that success. For a geometric model, we are going to eliminate B because they're waiting to find 2 people who have taken statistics. That is not exactly what a geometric model is. You're only a little late, Kyle. That's true. Anyway, the answer's got to be A. We got plenty of statistics to go. Number 9. Batco, a company that sells batteries, claims that 99.5% of their batteries are in working order. How many would you expect to buy on average to find one that does not work? To find one that does not work implies a geometric model. It implies a geometric model because you're waiting to get that first quote unquote success. Now, in this case, they're trying to find one that doesn't work, which technically would be a failure. So we got to flip some things around. The probability of not working is 0.005 because they claim 99.5% of their batteries are in working order. How many would you expect to buy on average to find one that doesn't work? There's a 0.5% chance of it not working. Now, how many would you expect refers to the average or the mu of a geometric. And the formula for the mu of a geometric is 1 divided by p. If you did 1 divided by 0.005, that gives you the number of trials that you would have to go through until you got that first success. Or in this case, the first battery that does not work. A success is not necessarily a good thing. A success is what you are looking for. Kyle chose B. Sorry, Kyle. Let's take a look at number 10. There it is. Some marathons allow 2 runners to split the marathon by each running a half. Alice and Sharon plan to split a marathon. Alice's half marathon times are 92 minutes with a standard deviation of 4, and Sharon's half marathon times are 96 minutes with a standard deviation of 2. Assume that the woman's half marathon times are independent. Now, this is key. This is very key. They tell you that the women's half marathon times are independent. They have to be. If they were not independent, or if this were a problem where we could not assume independence, then the answer would be E. It can't be determined. Because the problem's asking for the standard deviation, you are only allowed to combine their standard deviations if the 2 events in question are independent of each other. And yes, Alice's standard deviation, or marathon times or whatever, and Sharon's are independent of each other. They already combined their average marathons to get 188 minutes, the expected time. But if you want expected standard deviation, you are going to have to combine them. Now, that's 4 minutes and 2 minutes. But the rule for combining standard deviations, whether you are adding them together or subtracting them, it does not matter. You're going to have to convert them to variance, then perform the appropriate calculation, then convert them back to standard deviation. In that sense, the standard deviation, the combined standard deviation, should be 4.5. And I can show that calculation right here. Square root 4 squared plus 2 squared, 4.5, approximately. Now, if you were finding the difference between them, what is the standard deviation of their differences, or difference in times, or whatever you want to call that? It would still be 4.5. Not a typo. The calculation for the difference in standard deviations, when you convert them to variance, you still have to add them. And that's all in my formula test review. Let's talk about number 11. Passing the test. Assume that 70% of teenagers who go to take the written driver's license test have studied for the test. Of those who study for the test, 95% pass. All right, hold on. I'm not even going to read the rest of the question just yet. I got to take care of that statement. Of those who study for the test, 95% pass. The probability of passing, given that you're only looking at those who study, is 0.95. Okay? Of those who do not study, 60%. Okay? The probability of passing, given you don't study, 60%. Now, that given statement means a lot. I didn't do the 70% one. Assume that 70% have studied. Okay. The probability of just flat out studying, 70%. Now, what are they asking me? What they're asking for, what is the probability that a teenager who passes did not study? Now, this, what I'm writing, is the question that they are actually asking me. What is the probability that a teenager, given that they passed, did not study? This problem is asking me to take the probability of passing given no study and actually flip it to be the probability of no study given passing. No, Kyle, the answer is not 10%. It's not 15%. You're not going to like what the answer is. You can keep guessing all day long. You're never going to get it. Just watch what I'm going to do here. As my AP students are fond of doing, this problem deserves a probability tree. First of all, we can split it into those who study and those who do not study. 70% study, which implies that 30% do not study. Kyle, you forgot about decimals. Because I'm going to go 3 decimals on this. Anyway. Now, from the study branch, 95% pass given that they study, or given that you have already gone down the branch of studying. If you have studied, 95% pass, and 5% don't pass. These given statements mean everything. Now, given that you don't study, you have a 60% chance of passing, and it is implied a 40% chance of not passing. This is why we need the probability tree. This calculation, this, which I'm blocking off right here, no studying given passing, has to do with the formula. I shouldn't have read that. The probability of B given A is equal to the probability of A and B divided by the probability of A. That is a formula that is given to us on the formula sheet. Move that up just a tiny bit more. There we go. Now, the way that we're going to use that, we'd have to find the probability of not studying and passing, and implies multiplication, which is what we're going to do down this branch right here. In fact, let me do it in green so you can see a little bit better. This is the probability of no study and passing. If you multiply the two of them together, you get 0.18. That would be the top of that fraction. But on the bottom of that fraction, we would need the probability of passing. Now, the probability of passing, there's 2 options. You passed if you studied, or you passed if you didn't study. Watch what I'm going to do here. I went down another branch, study and pass. If I can multiply the two of them together, what did I end up getting? I got 0.665. So the probability of study and passing was 0.665. Those are the only two decimals that I need. I need this decimal, 0.665, and I need this decimal, 0.18. The probability of not studying and passing is 0.18 divided by the probability of passing, which is either 0.665 or 0.18. And when I say it like that with that word or, that does imply adding the two of them together. This is the calculation that I need. Bring this in. 0.18 divided by 0.665 plus 0.18. Notice the parentheses around the bottom of the fraction. That's my answer. You can't see it. I'm going to move the camera over. Or no, I'm going to move the paper over in a moment. But I wrote it as 0.213. Kyle, the answer was 21.3%. That's what we have to do for this problem. You have two options for my AP students. You have two options if you need to take something like this and flip it around. Instead of the probability of A given B, you're asked to be given the get the probability of B given A. There's a formula in the textbook that I do not like. Nobody likes it. Nobody uses it. Kyle, your answers are time-stamped. Hey, look, it's Joe. It's okay, Joe. I got plenty of time. I mean, I got plenty of problems to go over. But anyway. But that is what the answer is. Let's talk about number 12. Put this paper up a bit. You believe that there's a 20% chance of getting an A in your English class. There's a 10% chance of getting an A in your physics class, and a 5% chance you'll earn an A in both classes. Okay. Find the probability that you do not get an A in either. Meaning you don't get an A in English and you don't get an A in physics. That's a weird way of putting it. The way that I would do this problem, the honest, easiest way that you could potentially do this problem is by creating a Venn diagram. Yes. I'm just double checking what my notes are here. Or you could do it that way too. Okay. There's two ways of going about this then. I'm going to do the Venn diagram and I'm going to do the other way of doing it. If you're talking about Venn diagram, you'd say that this is English and this is physics. I'll think about it, Joe. I may have some things to do this afternoon, but I'll think about it. Oh, goodness. Anyway. Oh, actually, Joe, total side note. I'm going live tomorrow from, I want to say a little bit before 1. Like, I'll probably be going live around like in the 12 o'clock hour until like 3 something, because tomorrow is a cubing competition online. So I'll be on for probably a good 2 or 3 hours tomorrow. So let's just say I'll do that instead of going live today, because I got a lot of stuff to do today. So, sorry, back to this. The probability that you'll earn an A in both classes is 0.05. I'm going to put the 0.05 right in the overlap. The chance that you earn an A in English is 20%, which means that it's 0.15 in this portion, 10% in physics, which means it's 0.05 in this portion. If you were to add those up, clearly you get 25%. There is a 25% chance that you will get an A in English or physics. But this problem is asking to find the probability that you don't get an A in either class. The answer is 0.75. Another way of thinking about it, you could use that formula, the probability of A plus the probability of B minus the probability of A and B, which gets you 25% or 0.25. But since it's asking you don't get an A in either, you could do 1 minus, which gets you 0.75. Whichever way you slice it, the answer is 0.75. Part B. Are earning an A in English and earning an A in physics disjoint events? Disjoint is also known as being mutually exclusive, meaning they share nothing in common. There's no overlap between the two events. But clearly there is overlap between the two events. The way that I know that is because I looked at the Venn diagram. Clearly there's overlap between the two events. So are they disjoint events? No, because, well, this calculation right here, if they were going to be mutually exclusive, I could write that over here, if mutually exclusive, then the probability of both equals 0. If they're mutually exclusive, then the probability of both should be equal to 0. Clearly they're not. Part C. Are they independent events? Now, there's a couple different ways to identify them being independent events. In fact, there's 2 specific definitions. If independent, then the probability of A and B is equal to the probability of A times the probability of B. Another way of looking at that, if they're independent, then the probability of B is approximately equal to the probability of B given A. Again, multiple ways to look at it. We could say, okay, the probability of physics, according to the problem itself, is 10%. Okay, so the probability of physics is 10% versus the probability of physics given English, which we'd have to do that calculation that we did on number 11. If we did the calculation that we did on number 11 using this formula right here, then the calculation would come down to this. The probability of both, which is 0.05, divided by the probability of English, which is 0.20. I don't even know why I'm using a calculator right now. But this is equal to 0.25. This shows that they are not independent events. They are not independent events. Can't do anything about it. Another way of looking at it, like I said, was this one right here, the probability of A and B, which we know is 0.05. They give it to us in the problem, should be equal to the multiplication of those two events. If you do 0.2 times 0.1 or 20% times 10%, you get 0.02, which also shows that they're not independent. Not independent events. And what I have right here shows that. Joe, you have another joke? Do I want to know your other joke? Oh my. Al, you should be scared. No, you don't. I've had to block you several times. Back to this. Number 13. According to the National Health Survey, heights of adults may have a normal model with a mean of 69.1 for men and 64 for women. The respective standard deviations are 2.8 and 2.5. Based on this information, how much taller are men than women on average? Well, if we're expecting men to have a height of 69.1 and we're expecting women to have an average height of 64, if you're trying to figure out, well, how much taller are they? The expected value of men minus women would just be 69.1 minus 64, which is equal to 5.1 inches. Standard deviation for the difference, not a typo, you would have to convert their standard deviations to variance, add them together, and then convert them back. So you'd have to, for standard deviation of the difference, you would have to do 2.8 squared plus 2.5 squared, square rooting them. Gives you approximately 3.75 inches for the standard deviation. Now, we need those two calculations to answer what they're asking in part B. Assume the women date men without considering the height of a man, i.e. that the heights of the couples are independent. Now, that's key. They have to be independent. You have to assume independence and has to be reasonable. Now, in real life, there is a subconscious effect where, on average, the man is taller than the woman. But they want to know, assuming that the heights are independent, what is the probability that a woman dates a man shorter than she is? Now, if you're talking about the men minus women and the woman being taller, then we're looking at all values that are less than 0. If you go back to the description of this problem, they do tell you that it is a normal model. And since this is a normal model that we are dealing with, we are allowed to use Normalcdf. In fact, the calculation that we're allowed to do, something along the lines of this. We're trying to find the probability, which in this case, we're using the normal probability function, of women being taller, meaning we're looking at the value being less than 0, being negative, because we did all these other calculations as men minus women. Small number comma 0 will take that normal distribution in the negative direction with a mu of 5.1 and a sigma of 3.75. We did that calculation. Normalcdf, small number, comma 0, comma 5.1, comma 3.75 gives you approximately 0.087 or 8.7%. There's an 8.7% chance approximately of a woman being taller or the man being shorter, whichever way you want to word that. Let's talk about number 14. Number 14, according to InfoPlease, 18.8% of the luxury cars. Sorry, I was reading something. Oh, you're waiting for me to say something. I'm not going to say anything. 18.8% of the luxury cars manufactured in 2003 were silver. So, now we're only talking about luxury cars, but the probability of silver is 0.188. A large dealership typically sells 50 luxury cars a month. Joe, I don't know, and I don't think I want to know. Whatever answer you give, I get the feeling I'm going to have to block it. All right, back to my problem. Explain why you think that the luxury cars can be considered Bernoulli trials. Now, I talked a little bit earlier. There's Joe's joke. And remove. There he goes. Back to me. Bernoulli trials I talked about earlier. Bernoulli trials have to be independent. One has to be independent of the next. Bernoulli trials, there has to be definitive success and failure. Now, in this case, yes, they are Bernoulli trials, but for more reasons than you think. Now, first of all, there is a success, which is a silver, and failure, not silver. Let's see. And remove. There we go. More than that, we're talking about Bernoulli trials. Trials are assumed independent. Now, there's a couple different ways to think about this. You could think about it as each person coming in, whether or not they're going to purchase a silver luxury car or not, is independent of the next. But 18.8%, we have to, assuming the 18.8% is constant. Obviously, if you're talking about one particular dealership and there's a finite number of silver cars, then obviously that 18.8% is going to change every time somebody purchases one or doesn't purchase one. But we're assuming that the 18.8% is constant, and that allows us to assume independence. 50 is less than 10% of, I'm going to say, car population. Yeah, let's say dealership car. Yeah, dealership population. Dealership population. Yeah, we can say something to that effect. That's allowed. Yeah, and there's a lot more details that you can go into. Mainly, it comes down to the success and failure and the fact that the 18.8% is assumed to remain constant. Part B. What is the probability that the 5th luxury car sold is the first silver one? Part B is dealing with a geometric model, waiting for that first success. Now, since we're talking about getting that first success, you have to talk about the first 4 being failures. Now, in this case, you have an 18.8% chance of success getting a silver one, or a silver one being sold, and you have an 81.2% chance of it not being silver. You could do this problem in one of 2 ways. The first 4 cars are not silver, and then the 5th one is. If you do this calculation, 0.812 to the 4th power times 0.188, it gets you approximately 0.0817. 0.0817. Now, you could do it as geometric as well, in which the geometric model, you're trying to get the first success on exactly the 5th trial. So it would be a geomet PDF. There's a 18.8% chance of success, and you're trying to get that success on the 5th trial. Now, if we're correct, we should get the exact same decimal that we just got before. Geomet PDF 0.188, 5. Clearly we do. Part C. Let X represent the number of silver luxury cars sold in a typical month. Now, 50 luxury cars are sold, but we're saying let X be the number of silver ones. What is the probability model for X? Specify the model and tell the mean and standard deviation. For this problem, this model is going to be binomial. They're talking about a set number of trials, X being the number of successes, that we're looking at, which is a silver car being sold. There is a probability of success, but this is a binomial model. Now they want the mean and the standard deviation. The mean of a binomial model would just be n times p. This would be the expected number of successes, which in this case, mu is equal to 9.4. The standard deviation, sigma, I'll put n times p, is equal to the square root of npq, which if we did that calculation, square root 50 times 0.188 times 0.182 gets you approximately 2.76. Specify the model, name the parameters, tell the mean and standard deviation. Number 15. Here we go. Homeownership. According to the Bureau of the Census, 68% of Americans owned their own home in 2003. A local real estate office is curious as to whether a higher percentage of Americans own their homes or own their own homes in the area. The office selects a random sample of 200 people in the area and to estimate the percentage of those people that own their own homes. Verify that a normal model is a useful approximation for the binomial in this situation. Now, if you're dealing with getting a normal model or verifying a normal model, you want to go about the exact same specifications that you do for hypothesis testing and confidence intervals. Now, let's check n times p. N times p, if you did 0.68 times 200, would get you 136. N times q would be 0.32 times 200, which is 64, which is greater than 10 successes, greater than 10 failures. We could say that 200 is less than 10%. Now it says 68% of Americans own their own homes. We're looking at 200 people in the area to estimate the percentage of those homes owned by the owners. So 200 would be less than 10% of people in the area. Random sample was stated. Owning a home or not is an independent characteristic. Just because you own a home doesn't affect whether or not your neighbor owns a home or someone else in the town owns a home. Something along those lines. You can even say the 200 is large enough, but this verifies it right here. Verified normal model. It's allowed. So now that you've verified a normal model, look at part B. What is the probability that at least 140 people will report owning their own home? Okay. Since we're allowed to do a normal model, I could do normal CDF. Now I'm actually going to show you two ways to do this. At least 140 means 140 or more with an assumed mean of 136. That was n times p. We did that up here. But then the standard deviation would be the square root of npq. npq. If you did that, normal CDF, 140, comma big number, comma 136, comma the square root of 200 times 0.68 times 0.32 gives you approximately 272, or 0.272. There's a 27.2% chance that at least 140 people will report owning their own home. Now, I said I was going to show you more than one way to do this calculation. 140 people out of 200 which is the decimal 0.7, but I'm just going to leave it at that fraction for a moment, comma, big number. That would basically be 70% or more, assuming that 68% is the mean. You could do it this way too, and I'm going to show you it's going to get the exact same answer. But the standard deviation for a proportion would be the square root of PQ over N. PQ over N. Normal CDF 140 divided by 200. I put comma, divided by 200, comma, some big number, comma, 0.68, comma, square root 0.68 times 0.32 divided by 200. Get you the exact same decimal. It's more than one way to do the problem. You can look at it from the count point of view, 140, 136, n times p, the binomial model, or you can look at it from proportions. It gets you the exact same kind of answer. Finally, in part C, get that up there. There we go. Based on the sample, how many people would it take for you to be convinced that a higher percentage of Americans own their own homes in that area? How many people? So we have to do the binomial route. Now, in this case, it would have to be unusually high. Unusually high to convince me, which means 2 standard deviations above the mean. 2 standard deviations above the mean. If that were the case, the mean, as we said, was 136, which was n times p, plus 2 times the standard deviation, which I never actually calculated, but it's a square root of NPQ. 136 plus 2 times the square root of 200 times 0.68 times 0.32 gives you approximately 149 and change, which if we're at 149, I wouldn't be convinced just yet, but at 150, it would take at least 150 people owning a home. That's what it would take to convince me in the context of this problem. 2 standard deviations above the mean. Now, that concludes the review that I wanted to do for AP Statistics. That concludes the lesson. For you guys that are watching, I know, Joe, you asked earlier if I would live stream today. Unfortunately, I cannot continue live streaming today. But like I said, tomorrow I am going to be live streaming cubing, in which I'm going to be doing various events, and I'll probably end up doing I'll have multiple cameras set up actually too. It'll be kind of cool. I'll have a camera set up for my phone, and I'll have a camera set up on the webcam, and I'll do those, and I'll have in between events, if I'm not like doing an event, or if I have like a spare 15 minutes, maybe I'll do a speed run of Mario Brothers or something like that. I don't know, but I have a few different things for tomorrow. But tomorrow it's check to see if I'm live in the late 12 o'clock hour, like 12:30 to 1 o'clock. Check around that time, I think. Actually, let me double check real quick before I say anything else. I want to double check my schedule for tomorrow. Tomorrow's schedule. Yeah, 1 o'clock is the welcome. So yeah, I'll probably be on between 12:30 and 1 o'clock. No, I'm not playing Minecraft. 12:30, 1 o'clock, and I'll be streaming probably until about 3:30 to 4 o'clock, somewhere in that range. It's a big day of cubing for me. So come, stop by, join us. We'll have fun. We'll talk. Joe will try to share inappropriate jokes, and I'll try not to laugh. But anyway, I'm gonna sign off. Thank you guys for stopping by, spending part of your afternoon here, and yeah, we'll see y'all another time.